Okay, so today what I'm going to be doing is I'm going to be going over how I solved number 2 on that 2017 free response. I'm not necessarily going to go over the grading rubric because 1, that's already accessible to you online, and 2, it's pretty arbitrary as far as the grading scheme goes. Like it tells you how they awarded points, but it doesn't give necessarily all of the ways that you can earn those points. So I'm just going to talk about the way that I solved it. So if we look at the problem for that number 2, okay, we see that the student wants to determine the coefficient of static friction between a long flat board and a small wood block. Describe an experiment for determining the coefficient of static friction between the wood board and the wood block. Assume equipment usually found in a school physics laboratory is available. Draw a diagram, make sure you label and describe the procedure. So conveniently enough, we did a lab exactly like this. Yeah, we did it way back in the first semester. And what we did with that, if you need your memory refreshed, is to start on letter A, okay? What we did was we set up a wooden board, right? And we had it at a certain angle, okay? And we placed the wooden block on top of the wooden board. Okay. So I'm labeling. And the thing about this is that the only thing that we actually needed to measure in that experiment was our angle at which the block started to slip. And make sure that you include how to do that. Yes, you will be awarded points for going ahead and, saying that you used a protractor. So if you wanted to do your experimental setup, right, here is part 1. And here's part 2, is where we start to actually go up into it. So here's what I said. I said to set up the physics ramp, stand, my bad.
When the ball does get a little behind her, and some of it doesn't have a ton of margin, not a lot of roll or topspin on that side, so you're going to see a few errant balls flying out.
So all I'm doing here is just, of course, recalling what we did in that lab. And the prompt also told you to make sure that you reduce experimental error. So the way I'm going to do that is by testing at multiple heights.
17 years of age last year, at this time is when she was really starting to play some terrific tennis. Got to the 4th round at DP Wells, beating Kvitova and then losing to Pliskova. A wild card in Miami.
So you always want to do multiple trials anytime that you're doing an experiment like this, and you want to make sure that you're testing at multiple heights also to make sure that the height from which you slide that block isn't affecting the coefficient of static friction. Okay, pause the video if you need to get anything down from here, because I'm going to clear the board and I'm going to move on to the other parts of the problem. So Now we actually want to derive the equation for the coefficient of static friction in terms of quantities measured in the procedure from part A. So the best thing to do, and here's what I did, is to draw your free body diagram. Yay! Okay, so we have our point here, which represents our block, okay? And it's on an incline, right? We got to remember that. So we have mg pointing in that direction. It's on an incline, so we know that the normal force is going to be pointing in that direction, and the frictional force points opposite of the object's direction of motion. I'm going to include kind of the incline here, right? But this is obviously like not part of the free body diagram. And since we're on an incline, you know what that means? That means that we need to break this up into components. Yay! So I'm going to draw my same free body diagram. So we have our normal force and we have our frictional force. But we've got to break mg up into components. So I'm still going to draw mg. But I'm going to break it up into its components. So we have one component of mg going that way and one component of mg going that way. So because, I mean, this is just something that I kind of tried to beat into your minds. Okay, remember we're just multiplying by the trigonometric function that is correct for that direction. And now we're going to go ahead and try and solve for mu. We are looking for mu, and that's the coefficient of static friction. And I don't know what that means. Sync status disconnected. Oh, huh. Looking for mu. Okay, so the way that I'm going to do that is by using my equation that I know mu already stands for, and we know that the frictional force is going to be equal to mu times the normal force. Okay, and I just need to go ahead and I need to figure out what these two things are equal to. And the way that I'm going to do that is by setting my, using my Newton's second law, right? And setting things equal to each other. So if we're measuring the coefficient of static friction, okay? Static friction means that the block is not moving. So if the block is not moving, my forces are balanced and my net force is going to be equal to 0. So that means that the forces that are opposite one another are all going to be equal. So that means what I'm going to do is I'm going to set mg cosine of theta equal to the normal force. And I'm going to set mg sine of theta equal to the frictional force. And from there, what I'm going to do is I'm just going to go ahead and solve for our mu, right? And to do that, all I have to do is divide both sides by the normal force. So I end up with a frictional force over the normal force is equal to mu. So now we plug in these values, right? So my frictional force was mg sine theta. Normal force was mg cosine of theta. Everybody brought mg to the party, so we end up with sine of theta over cosine of theta, which is just equal to tangent of theta. And I'm pretty sure they would give you credit for something like this because it's still a mathematically valid statement to make. But just so you're aware, sine over cosine is equal to the tangent, so our derivation is just that answer, right? But you need to, of course, show all of your steps for your derivation. You can't just write this and expect to get full credit for it. Okay, now we're going to move on to part C. So pause the video, get anything down that you need to get down, and we'll go back to part C and we'll go ahead and read that. Okay, so now we have some lab groups. We're testing the hypothesis that the coefficient of static friction between the board and the block equals the coefficient of kinetic friction between the board and the block. And each group determines the coefficients, and the group's results are shown below, and we have some class averages. Okay, so based on these data, what conclusions should the students make about the hypothesis that the coefficients of static and kinetic friction are equal? Okay, now we can kind of rely on our own scientific knowledge here, right? We don't necessarily want to just look at the class averages and say, oh yeah, those are the same. So definitely they're going to be the same, okay? Your correct answer is that the coefficient of static friction is not going to be equal to the coefficient of kinetic friction. And the reason that I provided for that was, you know, of course we can't trust the class average, right?
Definitely an issue with the toss there. An issue with the sun, for sure. Yeah. Oh, you can't miss that. Boy, Anisilova just rolled in the first serve. Especially when you know the server's probably seen some dots. Yeah, can't see the next ball.
Okay, so those class averages aren't really like scientifically valid ways to interpret the data, okay? We understand that these, okay, and we can also explain that scientifically, right? Not only is class average not always the best thing to look at whenever you're trying to interpret the data, we can also explain this from a perspective that whenever the block is moving versus whenever the block is not moving, the forces on the block are going to be different, okay? So that's what's going to let us know that, okay, because the forces are not balanced, that's going to give me a different value for mu. So there are different magnitudes of forces.
Never want to serve volumes. Good point.
And the way that I kind of proved this was by whenever we wanted to find our mu of S, we knew that the normal force was equal to cosine of theta mg, and our frictional force is equal to sine of theta mg. But if we're trying to figure out mu of k, we can't do that. We know that we have motion in the in this direction, right? So we still know that our normal force is equal to mg cosine of theta, but what's going to happen here is that the mg sine of theta minus the frictional force is going to be equal to ma, because we have motion going down along the plane. So this would not give same mu. I think that setting up the equations and proving it that way is definitely a good way for you to try and get all of your points on this one. Okay, last one we're going to do is D. Pause the video here if you need to get this down. And we see that D asks us, a metal disc is glued to the top of a wood block. The mass of the block disc system is twice the mass of the original block. Does the coefficient of static friction between the bottom of the block and the board increase, decrease, or remain the same when the disc is added to the block? Okay, we're going to go back to our reasoning for the, our derivation, right, for mu. So our derivation for mu was equal to tangent of theta. I don't see mass anywhere in that derivation. So the coefficient of static friction will remain the same Oopsie, on the okay, so we can prove that using our derivation from above. We can also prove it using just our basic scientific knowledge, where we state that mu sub s for any surface or surfaces only the surface type, right? We know that ice is definitely going to have a different coefficient of static friction than a wood block or sandpaper or something like that. Does not depend on the mass. So that's your solution to number 2. Make sure you're viewing this video after you've made your attempt at solving number 2. And now you can go ahead